recorded. Okay. So for example one, this is a fairly easy example, right? We know that on no load, E is equal to, oh, where's my, sorry. Why is my pen messing up? Or do I have it upside down? Okay, yeah. So on no load, we know that our E is equal to some function G of IF, right? And we also know that on no load, our no load voltage is approximately equal to our E, which is this, right? So for example one, we have a DC machine is connected as a shunt generator when operated at a rated speed of 1500 reps per minute. The open circuit curve is approximately given by E of, so this is our E is equal to G of IF. And then the armature circuit resistance is 0.14 ohms. And the shunt field resistance is adjusted to be 459 ohms. Find the no load terminal voltage. Okay, so let me just do this for now. All right. So we know that our E is equal to G of IF. And our open circuit curve, G of IF, has been given to us, right? So, and we also know that on no load, V is equal to, or is approximately equal to E. And we know that on no load, because on no load, we already know that V is equal to IF RF, right? Please, can you kindly mute yourself? So we know this to be true because on no load, this is what our shunt generator is going to look like. Terminal voltage, V here, by KVL is simply going to be taking this loop, right? If we take that loop, the armature branch goes away, and all we have is our series field resistance and then the resistance from the field. So we have V is equal to IF RF on no load, right? So with this being the case, then we can take our E of G, our E, our open circuit characteristics, 3, 6, 7 IF on 0.233 plus IF. And please, I'll be asking for you to like punch the values for me, okay? So that I don't have to now be using my calculator so that we can go faster. Okay, so this is equal to, we already know that on no load, our V is approximately equal to our E from here, right? So then we can just equate this to be equal to IF and our RF, which was given in our question. We have 459 ohms, right? 459 ohms. So if we make IF the subject here, right, we are going to get IF to be equal to, how do you even call it? IF is going to be equal to 0.567 amps. Please, here we just made IF the subject, okay? And then from there, now we have our IF. So we can substitute our IF back into our equation for no load voltage, right? So then, knowing our IF, we know that V is equal to 0.567 times 459, right? So our terminal voltage V on no load is quite simply just 260 volts, okay? Please, are we good with this question? I think when it comes to this question, a lot of us are already good, so I'm just going to continue. And let's move to page, slide 123, right? For the question on the lap winding. Slide 123. So please, I'll also be giving some notes. Okay, I'll be giving you some notes as we go on, some things that you should know. Okay. Maybe if we are to meet again tomorrow, I'll just compile everything and then give you some advice before your paper. Okay. So if we move to slide 1, why am I even scrolling? Yeah, we have an example on simple lap winding here, right? So please, I'm going to read the example first, and then I'm going to solve it. But please, are we all okay with the first one I did? If you have any issue, as I said, you can just unmute yourself and then let me know your concern. Okay. So, exercise 1 says the number of conductors in each parallel part of an 8-pole simple lap winding must be greater than 94 and less than 102. Okay. The number of slots per pole must also be greater than 12 and less than 18. Okay. So we know that what we have, and please for this example, right? With a question, we assume that the number of conductors per parallel pole must be even. Okay, it must be even. So if that's the case, then we know that our minimum number of conductors per parallel part is going to be 96, right? So this is going to be Z min. And then our maximum number of conductors per parallel part, Z max, is going to be 100. Okay. So with this in mind, we also know that the number of slots must be greater than 12. So our number of slots, X max, sorry, this is S min, but then S max it must be less than 18. So S max is 17, and then S min is, please, can you mute yourself? S min is 13. Okay, so the maximum and minimum number of conductors per slot, fairly easy, this one. We have for maximum number of conductors per slot, we are going to take the maximum number of conductors and then the minimum number of slots, right? So we have 100 on 13 as our maximum number of conductors per slot. And for this, we get, should I do the calculations myself or you do it for me? Because I want it to be interactive. Please, 100 on 13. Who can give it to me? Hello. 100 on 13. Please, I'm waiting, guys.
7.69.
7.69. So this is our maximum, right? So if it's our maximum, it means we can't go beyond 7.69, right? So we are going to take our maximum number of conductors per slot, knowing that we can't go beyond 7.69, and also knowing that our number of conductors per slot must be even. We are going to choose 6 as our maximum number of conductors per slot. Please, are you okay with this? Please, if you
Yes, sir.
send chat, I think I accidentally turned off my notification, so I won't be able to see. So like, let's just if you have any issue, just unmute yourself and then let me know. Okay. So then that means that for our minimum number of conductors per slot, we are going to take our minimum number of conductors, which is 96, divided by our maximum number of slots, which is 17. So please, for this one, what are we getting? Very quickly. 96 on 17.
5.6.
5.6.
5.647.
Okay, so 5.647. Okay. So with this one, too, we know we can't go below 5.647. So the next closest even number greater than 5.647 is going to be 6, right? So if we have Z max or Z on S max being 6, and then the minimum also being 6, then we can assume that we have 6, or we can't even assume, we conclude that we have 6 conductors per slot. Are we okay with this? Okay, that's fine. And then the question also says the number of coils per slot if U should be greater than 1. Okay, so we know we have 6 conductors, right? We have 6 conductors per slot, so we can just Hello. Please, apparently I heard I was muted. I'm just realizing that now. Please, can you hear me now?
Yes.
Yeah.
Oh, I'm so sorry. I'm not too used to modern technology. So please forgive me. Okay, so but are we okay with what we had so far up to the number of conductors per pool? Are we okay with it? Or should I go over what I said?
Please go over.
Please
Please
go.
go over.
Okay,
Yeah,
please,
go over.
from which point? Can you specify the
Please
point
go.
you need me to go over from?
The 5.647, that side.
Okay, wow, okay. But the 5.647, someone gave me the answer.
No,
So
like
that at
Yeah,
that point, I
that's
that
also
where
need
we
side.
to.
could hear you. The rest we didn't hear.
Okay. Oh, okay. If that be the case, then that was our maximum and minimum number of conductors per slot, right? So I'm continuing. So if we have our maximum number of conductors per slot to be 6, and our minimum number of conductors per slot to be 6, then we can take our number of conductors per slot to be 6, right? That's the point here. Are we okay with that?
Yes, sir.
But
Yes. Who is
like
speaking?
the 7.69, we rounded
Mhm.
down, and the 5.647 went up. Can you please come again with the reason?
Okay, so I went up because if we have a maximum number, right, being 7.69, then that means that we are not looking to go beyond 7.69, right? So then, if you are not looking to go beyond 7.69, and we know that we have even number of conductors in our slots, right? Then what is the next even number less than 7.69? Okay. Are you okay with what I just said?
Yes, please.
Yeah, and the same applies for the minimum. We know we can't go below 5.64, right? So if we can't go below 5.64, then what is the next even number greater than 5.64? And that's also 6. Okay. So with that in mind, I think, where do I continue from? I think we then go for our U, right? Says calculate, it says the number of calls per slot U. Oh, okay, the number of calls per slot if U should be greater than 1. Okay, so if U should be greater than 1, then we know that for 6 conductors per slot, right, we can either arrange them. We know that we have a 2-layer slot here, so we can either arrange them like this to get our 6 conductors per slot, or we can arrange them like this: 1, 2, 3 per layer, 1, 2, 3 in another layer, right? But then we also know that our U, number of coils per slot, is equal to the number of columns we have in our slot, right? So for this one, we have 1 column, and for here we have 1, 2, 3 columns, right? So how do I even continue? Yeah. Okay, so if we know that U must be greater than 1, and we know that U can either be 1 or 3, then our U, number of coils per slot, is equal to 3. Please, are we okay? Are we okay?
Yes, sir.
All right.
Yeah.
And then from there, the next question says we should find our number of slots per pool, right? Okay, so we know that we have, this is a lap winding, right? Let me just clean the arrangements I did here. So we know that this is a lap winding, so our number of parallel paths A is equal to the number of poles we have, right? And we have, we've been given our number of conductors per parallel path, right? So if number of parallel paths is equal to number of poles, then I can also assume and call it our number of conductors per pole, right? So if that be the case, then our number of slots per pole, our S per pole max, right? Maximum number of slots per pole is going to be equal to our maximum number of conductors per pole divided by our number of conductors per slot, right? And then S on P minimum, sorry, it's 2P, okay. 2P minimum, which is our number of slots per pole, is going to give us our minimum number of slots, sorry, our minimum number of conductors per pole divided by our number of conductors per slot. So 100 on 6, we have, how do you even call it? So for 100 on 6, we have 16.67 slots as our maximum. And then for our minimum, we have 16. So if we can't go beyond 16.67, our next integer is 16, right? So then we have 16 slots per pool. And already we're told that our number of slots per pool ranges from 13 to 17. And 16 is between 13 and 17. So, okay, I think, is there another question there? No, okay, so now we can go to exercise 2. Slide 124. Right. Exercise 2 says, yes, you have an issue.
Yes, please. So
What's your issue?
imagine the maximum number of conductors per slot and the minimum number of conductors per slot. We got different answers. If we're finding the number of conductors per slot, could we go about it differently?
You won't get different answers, okay? You won't get different answers because that is from that analysis that you are going to choose your number of conductors per slot. So ideally, you are going to get maximum to be the same, minimum to be the same, so that you can just get number of slots, sorry, number of conductors per slot to be the same, okay? The question will be framed in such a way that whenever you are asked to find maximum and minimum anything, you are going to get the same thing. So for here, we have a simple lap winding has the following particulars. C is equal to 384, E is equal to 4, and P is equal to 4. Okay. So at least 10 and not more than 15 equalizers can be used. Find the number of equalizers. This is a very simple question here. Should I clean and just use this page, or I should leave this page with a solution on it?
Don't clean it, use another page.
Hey, sorry, boss. Okay, boss, I hear. Okay, so we know that for equalizers, right, our relationship C on P times 1 on our number of equalizers must give us an integer, right? And we have our C to be 384. And we have our C to be 384. Hello. Yeah, I saw, I've seen, I've unmuted myself. Please, what point did I mute what point did my microphone get mute?
After you said
Must be an integer.
whatever is equal to
Oh, okay. So then what I'm saying is that C on P times 1 on the number of equalizers, right? For, how do you call it? For this relationship, our answer must be an integer. So with that in mind, if we use 10 equalizers, right? If we put 10 here, will we get an integer? If not, then we put 11 there. If not, then we put 12 there, because he said must be 10 and must not be more than 15. We said must, yeah, so whichever one that said there, you keep on substituting the values in until your relation gives you an integer. Okay. And then for this relation, I know that when our number of equalizers is 12, this relation will be true. Okay. So please check for me what we get when our number of equalizers is 12. Just punch this one in your calculator and then give me an answer.
A.
What did you get?
A.
Okay, so I hope we know that 8 is an integer, right? So that means that it's true. I think there's a problem with my microphone, and whenever I move slightly, it gets muted. So I'll be paying attention to that, right? Please, are we okay with this question? So you put 11 there and see if you get an integer. Okay, put 10, 11, 13, 14, and 15 there and see if you get an integer. Right? You are going to realize that you are not going to get an integer, you are going to get a decimal. And if that be the case, our relation is no longer true. Okay, so now let's look at a simple wave winding question at slide 135. Okay. So, exercise 3. All right. So the total number of conductors for a simple wave winding armature must be approximately 760 with a tolerance level of 5% allowed. So what does that mean? That means that our number of conductors, our total number of conductors must either be 760 plus, or it must be 760 plus or minus 5%. Okay. So maximum is 760 plus 5%. Minimum is 760 minus 5%. The number of slots ranges from 39 to 45. So please, with this question, I know that you guys, with your English, you are going to say that ranges from 39 to 45 means that 39 and 45 are included. But then please, I think it was a mistake in the wording, right? Because if you look at the solution, it does not include 39 and 45. Okay. So it's between 39 and 45. Okay. And the commutator bars are positioned between 117 and 135. Okay. So S and U must be odd. Why? So we must explain why C, S, and U for this, how do you call it? Must be odd. Okay. Please, can I start? Can I start with a solution?
Yes, please.
All right. Thank you very much. So we know that for a simple a simple wave winding, right? We must obey the relationship 2YC is equal to C plus or minus 1. C plus or, wait, it's not 2YC. Sorry, I'm so sorry here. Okay. It's, all right. So we know that for our simple wave winding, the relation P YC must be equal to C plus or minus 1, right? So with this in mind, P is our number of pool pairs, right? And the question says we have, where is it? 4 pools, right? The question says our number of pools is equal to 4. So 2P is equal to 4. So that means that we have 2 pool pairs, right? Hello. Hello. Hello.
Yeah.
Yeah, please, sorry. Okay.
We can't see the board.
Yeah, yes. I lost my internet connection. I'm now coming to share my screen again.
All right.
Please, can you see now?
Yeah.
Yeah, we can.
Okay. So, where was I? Right. So what I was saying was that for a simple wave winding, this relation must be obeyed, right? So if you have our number of pool pairs being 2, then YC is equal 2YC is equal to C plus or minus 1, right? So for this to be a simple wave winding, all we are trying to say is that C plus or minus 1 must be divisible by 2, right? Right? And so for C plus or minus 1 to be divisible by 2, then C must be odd. Because an odd number plus 1, then it becomes an even number and it's now divisible by 2. Okay. Please, are we fine with that explanation?
The screen is not showing.
Come again. I'm moving on. Oh. Okay. And we also know that C is equal to SU, right? And so for C to be odd, then it means that we know that an odd number times an odd number is going to give us an odd number, right? An odd number times an even number will give us an even number. An even number times an even number will give us an even number. So if we are saying C must be odd because C plus or minus 1 must be divisible by 2, then S and U must also be odd because S and U are factors of C. All right. All right. And then the next question says, to find the maximum and minimum number of conductors per slot. Right. Okay, so the question says we should choose the lowest. Oh, okay, sorry, I'm so sorry. Okay. So the next question says determine all possible numbers of slots, right? We know that our number of slots S is between 39, and 45, right? And we also know that our number of, so this gives us 40, 41, 42, 43, and 44, right? But then fortunately, we just found out that our number of slots must be odd from here, right? So if our number of slots must be odd, then our number of slots is either going to be 41 or 43. Are we okay? Are we okay? I'm moving on, guys. So and the question says, choose the lowest possible number of slots and use it to determine A, the maximum number of coils per slot, and B, the minimum number of coils per slot. Okay, so choosing the lowest possible number of slots, that means that we are taking our S to be equal to 41, right? Our S is equal to 41. So if S is equal to 41, and please let's remember, right, that our number of coils, C, is equal to our number of commutator bars, right? And the question says the number of commutator bars is between 117. So our question says C is between 117 and 135, right? And our question also from our first solution, we know that C must be odd. So we know that C minimum is going to be 119. And then C max is going to be 133, right? So if we are using 41 as our number of slots, then maximum number of coils per slot, U max, is going to be C, which is 113, C max on S, which is 41. And then our minimum number of coils per slot, U min, is also going to be 119 on 41. Okay. So please calculate U max and U min for me. Please, can you hear me?
Yeah.
Okay, so find U max and U min for me. Sorry, this is 133. Okay, it's not 113. U max is 133. So please, U max is going to be
3.24.
3.24. And we know that U must be odd. So we can just take U max to be 3. And then U min is going to be
2.90.
2.90. So we just take U min to also be 3. So if U max is 3, U min is 3, then U is equal to 3. Okay. So the person who was asking about if you are going to get different numbers. For a situation like this, where we would have gotten different numbers for S is equal to 41 and S is equal to 43, the question made us choose our S to be 41. You understand? So the question is always going to be framed in such a way that however you do the calculation, you're going to get the same number for maximum and minimum. Okay. So, moving on, we have the maximum number of conductors per slot. So, maximum number of conductors per slot, we know that Z max is equal to 760 plus 5%, right? This is 5% of the 760, okay? And then Z min is going to be equal to 760 minus 5%. Are we okay with this? keep in mind, the question still says we should take the lowest possible number of slots. So we are still taking S to be equal to 41. All right. So Z max is going to be 798, right? So maximum number of conductors per slot, I'm going to make it small Z max is going to be 798 on 41, which is, and then minimum number of conductors per slot, small Z min, is also going to be 722 on 41, right? So for here, we get maximum number is going to be 19.4. But we are going to, because it must be even, Z must be even, right? Number of conductors per slot must always be even. And how do you call it? Sorry, I lost my thought there. Z must be even and less than 19.4. So we are going to get Z maximum number of conductors per slot is going to give us 18. And then this one is also going to give us, for minimum, 17.6, right? So from here, rounding it up, we are going to get 18. So then we know that we have 18 conductors per slot, right? Please, are we okay with this one? Number of conductors per slot, are we okay? Guys, are we okay? Before I continue.
And
Are we
please
okay?
explain the 19.4 part again.
Okay. We are looking for, we know that our number of conductors, our total number of conductors in the machine is 760 with a tolerance of 5%, right? So that means that we can have a maximum number of conductors being 760 plus 5%, and the minimum number of conductors 760 minus 5%, right? So the question says we should take our number of slots to be 41, or he said we should choose our lowest possible number of slots, which is 41, and then use that one to find our maximum number of conductors per slot, right? So if that be the case, our maximum number of conductors per slot is 760 plus 5% of 760, which is going to give us 798 divided by the number of slots we are using, 41. We are going to get 19.4, right? So our maximum number of conductors per slot is giving us 19.4. But we know when we have a maximum number, we can't go beyond that number, right? And we also know that our number of conductors per slot, Z, small z, whatever, our number of conductors per slot must always be an even number, right? So then if we can't go beyond 19.4, then what is the next closest lower even number, right? Because if we round it down, we get 19, and 19 is odd. So we'll come down again and we choose 18.
Thank you.
All right. For our question B, it says, for the number of slots chosen in part C, so we are still keeping our number of slots to be 41, right? Determine A, the number of coils per slot. So we had U max to be 3. Number of coils per slot is equal to U. We had U max to be 3. We had U minimum to be 3 when we choose our number of slots to be 41. So then we can assume that, in fact, no, we can conclude that if U max is 3 and U min is 3, then U is equal to 3, right? And then the number of conductors per slot 2, if Z max is 18, Z minimum is 18, then Z is 18, right? And then the number of commutator segments, okay. Hey, wait, oh. Okay, yeah. The number of commutator segments. So I'm going on to continue with number of commutator segments, right? We also already know that our number of commutator segments is equal to our number of coils, right? So if we are still keeping our number of slots to be to be 41, and we found our U to be 3, then C is going to be equal to S times U, which is going to be 41 times 3. Are we okay with this? Are we okay with why our number of commutator bars is equal to C. Okay, so 41 times 3, we get 1, 2, 3 coils. So we know that our number of commutator bars is equal to our number of coils. So if S is 41 and U is 3, then our number of coils is 1, 2, 3. So we have 1, 2, 3 commutator bars in our machine. All right. Are we fine?
Yes, sir.
Okay. And then the question also says we are to find our commutator pitch, YC, if our winding is progressive, right? And we already know that for our simple wave machine, we have PYC is equal to C plus or minus 1, where it's plus for a progressive machine and minus for a retrogressive machine. So if P is 2, then YC is going to be equal to 1, 2, 3 plus 1 on 2, right? So our commutator pitch YC is going to be 62. Okay. 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 So please, are we okay with commutator pitch, like up to that point, before I continue? Are we okay up to that point? Are we okay up to this point? Please, let's be faster in our response. I want us to finish all the examples under simple lab machines today. Yeah, who has their hand
Yes,
up? Please
please.
talk, unmute yourself and talk. Hey, we're fine. Okay. Well, I'm continuing. Please, can I continue?
Yes, please.
All right, thank you. Determine the number of bottom conductors for coil 1 if its top conductors are given. No be Bernard. It's who class? Okay, please. Determine the number of bottom conductors for coil 1 if its top conductors is given the number 1. So all this question is trying to tell us that if for coil 1 we have top conductor 1, where will its bottom conductor be, right? So to do this, we need to know our coil pitch. Hey, sorry, how do we even call it? Oh, why should I frame it? All right. So first, we are going to look for our slot span, right? Our slot span, which is equal to number of slots divided by our number of poles. But it can't be my baggage. It's tough. So our slot span is equal to S on 2P. For a 4-pole machine, we are going to have 41 on 4. So our slot span is going to be 10.25, but we take it to be 10, right? We take our slot span to be 10. So that means that if top conductor 1 lies in slot 1, then its bottom conductor is going to lie in slot 10. Okay. So now we must find our coil pitch YB, which is going to be the actual bottom conductor number. So YB is equal to slot span times U, right? So YB is equal to slot span times U. We have slot span to be 10. How do you call it? U to be 3. So our coil pitch is going to be 30. So that means that if we start from coil 1, then its bottom conductor is going to be 30 conductors away from it. So its bottom conductor is going to be bottom conductor 31, right? So for top conductor 2, its bottom conductor is going to be bottom conductor 32. For top conductor 3, its bottom conductor is going to be bottom conductor 33, and so forth, right? And the question said we should find for top conductor 1. So bottom conductor for top conductor 1 is going to be 31. Okay. Please, are we okay with this? All right. So the last part of the question says, show by diagram how the conductors are arranged in a slot and use it to determine the number of turns in a coil. Okay. So we know we have 18 conductors per slot, right? And we have U to be 3. So for 18 conductors per slot, we have a 2-layer slot. If we have a 2-layer slot, then that means that we must have 6 conductors per layer, right? Because if our number of rows is equal to 3, right? If our number of columns, U, is equal to 3.
Yeah.
Yes. Hello. Hello,
Yeah,
guys.
please, can you go through question?
Hey, say go over. Please, who wants me to go over, and where do you want me to go over from?
Question E.
Question what?
E.
E. E for Emmanuel.
Yes, please.
Okay. Please, I'm going over question E. Okay. Question E says, determine the number of bottom conductors for coil 1 if its top conductors are given the number 1. Okay. So we know that for a machine, right, if our top conductor is in a slot here, the bottom conductor making up that coil is going to be in another slot. It's going to be here, right? So this is how our coils look like in a machine, right? Top conductor here, bottom conductor here, right? And now our question is saying, for our top conductor 1, where will its bottom conductor be? Or what will be the number of its bottom conductor? Okay. And so to get that one, we need to know our commutator pitch. Our coil pitch. Okay. We need to know our coil pitch, which is the distance from one conductor or from the top conductor of one coil to its bottom conductor. Okay. So our YB, which is our coil pitch, is equal to our slot span times U, right? We've already found U. We need to find our slot span. And our slot span is also equal to our total number of slots divided by our number of poles. Okay. So our slot span is quite simply the distance between adjacent slots for the same coil, right? So if I am coil 1, and my top end is in slot 1, my bottom end is going to be the slot span away from slot 1. And we got our slot span to be 10. So if I am coil 1 and my top conductor or my top half lies in slot 1, my bottom half is going to lie in slot 10, right? And then we find our coil pitch, which is just trying to say that if I am coil 1, then my top conductor lies, or my top conductor, I call it top conductor 1. Then my bottom conductor is going to be a coil pitch away from my top conductor, because the coil pitch is the distance between top and bottom conductors of the same coil, right? So if I get so right now we got our coil pitch to be 30. So what does that mean? That means that for top conductor 1, it's bottom conductor is 30. So if I am number 1 and my partner is 30 away from me, then my partner is going to be number 31. Are you cool now? Are you cool now?
Yes, please.
All right. So now it says, how will it be arranged, right? Okay. We already know our number of columns, right? Because the number of columns is equal to U. So we need to know our number of rows, and we also know how many conductors per slot, right? It's 18. So then our number of rows is just going to be 18 divided by 3, right? Which is going to give us 6. So we have 6 rows. So we have 3 columns, 6 rows. So column 1, column 2, column 3. We have row 1, row 2, row 3, row 4, row 5, row 6. Please, are you okay with this? Are you okay with this? Okay. So then if we have 6 rows, 3 layers, 6 rows, 3 columns, then we are going to have conductor 1, 2, 3, 1, 2, 3, 1, 2, 3. And then we are going to have the same in the bottom layer. 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? Are we fine? Okay. And then it says also to determine the number of turns in a coil. Please, the number of turns in a coil is just simply the number of rows per layer, right? So we have 3 rows per layer. So this is a 3-turn coil. Okay. 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 All right. Please, I'm going to the next question. Since no one is minding me, I'm going to assume that we are all okay. Then I'll move to our next question. All right.
Yes, please.
Oh. So yeah, the exercise 4 is the same as the other exercise, the first exercise in the simple lap winding. Okay, so I won't do that one. I've already done it. Okay, guys. Please read this. Okay, read this before the exams. Okay, basically, all it's trying to tell us is that for a simple lap winding, we get more current, less voltage. And then for a simple wave winding, we get more voltage, less current. But then the same power. So for the same power, we get more current, less voltage for simple lap. So let me see if I can just explain it quickly, okay? So with this one, all our windings are contributing to give us current, right? So we have 6 windings. So current is going to be 6I. The current in all 6 of them combined to give us the current. Meanwhile, because they are in parallel, the same voltage goes across them, right? So our voltage here is E. So our power is going to be 6EI. And then for here, for our simple wave winding, we know that our number of parallel paths is equal to 2, right? Because it can either be clockwise or anti-clockwise. Okay, so if we have 2 parallel paths, then we are going to have a voltage. Because these are all in series, our total voltage is going to be the voltage E across here. I hope you can see my mouse. The voltage E across here and then the voltage E across here, giving us 3E. And then our current is going to come from both parallel paths, giving us 2I. So for the same power of 6EI, a simple wave winding will have a greater voltage, whereas a simple lap winding will have a greater current. Okay. So I just wanted to explain that quickly. Okay. And then also for here, I think some people were confused. So I'll address that issue. Let me address that issue right now. Right. With the A is equal to 1. I think some people were having concerns with why we say our A is equal to 1 when we are saying our number of parallel paths is 2. So please, are we all okay with that? Or I should just address this right now?
Please
Address it.
address it.
Okay. So please, do you want IPv4 or IPv6 addressing? Please don't mind me. Okay, let me address it right now. Okay. Let me open a blank sheet. All right. So we know that our equation is E is equal to Z, number of conductors per slot, phi P, flux per pole, NM, oh, what did you do? NM, which is our speed, the speed of our motor, our generator, sorry. And then P, which is our number of pole pairs, right? All out of 60A, right? So we know that our number of parallel paths A is equal to 2 for a simple wave winding, right? And we have 2P being our number of poles, right? So with that in mind, in some books, you see that they use the P here as number of poles, okay, not number of pole pairs. So if you use the P here as number of poles, A is still going to be 2, right? But the number of pole pairs is already number of poles divided by 2. So instead of using number of poles and then making A2, he just makes A1 and then he uses the number of pole pairs. So he just treats it like the A has already divided the number of poles to give us our number of pole pairs. Please, are you okay with what I just said? Are you okay with what I just said? Please, are we okay with what I just said? Yes, who has raised their hand? Unmute yourself and speak.
Sorry, yeah, it was a mistake.
Oh, okay. So if you want to use A is equal to 2, basically all I'm saying is that if you want to use A is equal to 2, then use number of poles in your equation, okay, so that the 2 will just divide the number of poles. But if you want to use number of pole pairs in your equation, use A is equal to 1, okay? So if it says an 8-pole machine and you write Z phi P N M times 8, then you make your A equal to 2. But then if it says an 8-pole machine and you use P to be equal to 4, then you make your A equal to 1 because you've already done that division. Okay. All right. So what I'm going to do for these examples, some of these examples, is because they already have the steps laid out in the slides, I'm just going to circle the steps and talk about them rather than, sorry guys, rather than rewrite the steps again. I hope that's fine with all of us. Hmm. All right. So, example one, a 3 kilowatt 4-pole lap wound DC machine is equal to 30. Then I'm making a 3 kilowatt 4-pole lap wound DC machine has 32 poles of conductors. So you have 12. The machine has a mean air gap diameter of 10 centimeters and a length of 12 centimeters. The field winding is wound on stator pole spanning 68 degrees. The maximum air gap flux density under the field poles is 1 Tesla. If at rated load, the armature draws a terminal current of 40 amperes. Determine A, the rated torque, B, the rated speed, C, the rated terminal voltage. Okay, the armature resistance RA is 0.4. The voltage drop across each brush is 1 volt. So we are not neglecting voltage drop across the brushes, okay? And please know the formula for current loading. A is equal to S times Z IW, blah, blah, blah. Know that one because in your midterm, he didn't give that. Okay. All right. The torque equation is also just the same equation being written from here. Where is it, stuff? Yes. So this is our torque equation. Right. So this is the equation he's using. Okay. So we have our number of slots to be 32. So we have our number of slots to be 32. We have 12 conductors per slot. And IW is just our current per conductor, right? So each conductor is carrying 10 amps of, let me see. Yes, each conductor is carrying 10 amps of current, right? From here. The current in our armature divided by, because it's a lap wound, we know that number of parallel parts A is equal to number of poles, right? So each conductor per pole is carrying 10 amps of current, okay? And then this is our radius. And here we have, how do we even call it? Pi, okay? So please, the current loading formula is straightforward. You just substitute your values in, and then you punch into your calculator, okay? And then torque is equal to 2 times lambda f. Lambda f is our pole pitch. Is it sorry, pole length? Okay, is our pole length, and then phi lambda p is our pole pitch, right? So we know we have 4 poles. This is a, how do you call it? We are looking at a rotational machine, right? So the poles is going to be 360 degrees, right? That's going to be the total distance we have. So 4 poles distributed in 360 degrees. Each pole is going to be 90 degrees away from the other. Please, are you okay with that? That is why we have our pole pitch here being 90 degrees, right? So from there, once again, you just substitute your values in. B is flux, it was given. Flux density was given. A is current loading, we just calculated for it. Pi is pi, R is radius, it was also given. And L is length, it was also given, right? Because we know that torque is B even. So this is volume, right? Area times length will give us volume. Okay, so you just bring your parameters in, you substitute everything in, you punch it into your calculator. Very simple, right? All right. Sorry, please, if I'm rushing, I'm not really feeling too well. So, like, talking has become a bit hard for me. That's why I'm rushing through a bit of the statements. Okay. And please remember, yes, before I forget, how many people are even in, how many participants do we have right now? However many participants we have right now, please, let's vote for NK, okay? He's the one who supplied the tablets, the data, everything. So please, let's vote for NK. If you don't vote for NK, I'll meet you in the marking room. Please, I'm joking. I'm joking. Yeah, we have 90 participants. Please, the 90 of us, we are voting for NK. I beg you. He's doing a very good job. And then, yeah, for speed. So this is for talk, right? It says we should find our rated speed. And then for speed, we know that for a given power, right? For electromechanical conversion, EA, IA must be equal to TE omega M. What am I saying with this? All I'm trying to say is that electromagnetic power must be equal to mechanical power, right? We have our electromagnetic power to be 3,000 or 3 kilowatts. It was given to us. Yes.
Electromechanical.
What do you mean?
You were saying electromagnetic.
I mentioned electromechanical. Listen, okay, so let me take it over again, okay? Okay. What I said was that for electromechanical energy conversion, right, electromagnetic power, PE, must be equal to mechanical power, PM. Okay, that's what I said. Are we okay now? Are you okay now? Was that David? All right. So PE must be equal to PM, right? And we know our PE to be 3,000 or 3 kilowatts. So it must be equal to our PM, which is torque times speed, right? And we found our torque. So our speed is just going to be our power divided by our torque. And then we have our speed in radian per second. Okay. All right. And for our terminal voltage, because we were given, how do you call it? We're given the voltage drop across our brushes. Okay, let me see if I can just draw how the machine looks like so that we can get the one there. All right. So, okay, I won't draw. Okay, I'll just use the drawing we already have here. Where is it? Where is it? Where is it? Where is it? Oh, it's too far up. Okay, let me just draw. So for our armature circuit, we know that we are going to have, you know that we are going to have a circuit of nature with terminal voltage VA, right? So, yeah, we're also going to have a commutator brush here, So we have RA, LA, but then the question didn't give us an LA, so we take LA to be 0, right? So a VB, a drop across this brush, and then VB, a drop across this brush as well. And then we have our induced EMF E, right? So from here, using KVL says sum of sources is equal to sum of drops, right? VA is equal to some current IA times RA plus the voltage drops across our brushes 2VB plus E, right? So now we have IARA. IA was stated in the question. RA was stated in the question. Drops across our brush was stated in the question to be 1, right? So now we must find our EA. And once again, for electromechanical conversion, we know that EAIA is equal to TE omega M, right? So we just make EA the subject here, and then we can find our EA, right? So that's what's being done here. Okay. And we substitute everything back into it. We get our terminal voltage to be 93 volts. Please, are we okay with this explanation too? Are we okay with this explanation? Please, are we okay? Can I move on? I'm moving on.
Yes.
Okay. Example 2 says a 6-pole simple wave. So what we need to know there is that for a simple wave winding, A is equal to 2, right? Has 64 singleton coils and 32 slots. Draw a slot showing the arrangement of conductors. State whether the winding should be progressive or retrogressive. So this is 6-pole. And then calculate the slot span and coil pitch. Okay, so this is 6-pole, right? So if we have a singleton, how do you call it? If we have a singleton coil, right, then that just means that the number of rows per layer is equal to 1, right? And it's a 2-layer slot. So that means that our number of rows period is going to be equal to 2, right? Okay. So here's what? 64 singleton coils, right? Okay. So you know that our number of rows is going to be equal to 2, right? Because singleton coils, one row per layer, 2 layers. We have 2 rows. Okay. And then what again? We have our C, we have our S. So we can find U, which is going to be our number of columns, right? So we know that U is equal to C on S, right? C is 64, S is 32, right? If C is 64, S is 32, then 64 divided by 32, we get 2. So now we know that we have 2 columns, 2 rows, right? So what does that mean? That means that we are going to have, if we have 2 columns, 2 rows, then we are going to have 4 conductors per slot, right? He decided to divide the number of, he decided to go about it with a different approach, but then this is how I am going about it, okay? We determine our number of rows. We can find our number of columns by finding our U, and then we just multiply them to get our number of conductors per slot, right? So for 4 conductors per slot, that means that we are going to have U being to 1, 2, 1, 2, 1, 2, 3, 4 conductors per slot, right? And that's what we have here. Okay. The first question was saying, draw a slot showing the arrangement. Okay, and then now the question says, state whether the winding should be progressive or retrogressive, right? So for this one, we know that PYC is equal to C plus or minus 1 must be an integer, right? So P is 3 because we have a 6-pole machine, okay? For a 6-pole machine, we have 3 pole pairs. So YC is equal to C, which is 64, plus or minus 1 on 3 must be an integer. So 64 plus 1 is going to be 65, right? 65 is not divisible by 3, right? So 64 minus 1, 63. That is divisible by 3. So we know that for this relation to be true, YC must be equal to 64 minus 1 divided by P. And if it's minus, then it must be retrogressive, right? And then the last part says calculate your slot span, calculate your coil span. We already know that slot span is equal to S on 2P. I've already mentioned this. And then we also already know that coil pitch YB is equal to slot span times U, right? So I hope this example is very understandable. I'm moving on to example 3.
Is that a
Yeah,
question?
what did you say? Yes, ask your question.
The big Z, could you go over it again? The times 64 times 2.
64 times 2. I didn't do it like that, okay? But then all it's trying to say is that we have 6 coils, right? We have 64 single 10 coils, right? So we know that C, which is our number of coils, is equal to our Z, number of conductors, divided by the number of turns of our coil, right? Hey, sorry, not divided by the number of turns of our coil. I don't know if you want to. You please let me explain it in my own words, okay? So just follow my explanation. Don't really pay much attention to this one, like for this one alone, okay? Because I am not finding the words to explain this one, okay? So I'm just going to explain it for you how I understand. So please, are you ready?
Yes.
Okay. So the question says we have 64 single 10 coils, right? And the number of turns per coil, right, is equal to the number of rows per layer. Okay, so if we have single 10 coils, then that means that each layer of our slot is going to have 1 row, right? So 1 row, we know that is a 2-layer slot. So if each layer has 1 row, then the whole slot is going to have 2 rows, right? Okay, our slot has 2 rows, but that doesn't help us identify what we want to do. What we know right now is our slot has 2 rows. So now it's left with columns. But we know that the number of columns in our slot is equal to U, right? And we know that U is also equal to C on S, right? So if C is 64, S is 32, U is equal to 2. So that means that our slot now has 2 rows, 2 columns. We are going to have 1, 2 here, 1, 2 here. So filling our slot now, we are going to have 1, 2, 2 rows, 1, 2, 2 columns. Do you understand me now?
Yes, please.
All right. So I'm moving to example 3. Hey. Here we go. Let me look at example 3. Please, can I skip example 3? It's just, how do you call it? It's just straightforward. You can just input your values in there. Everything you need has been given to you in the question. The only thing that wasn't given is the number of conductors, the total number of conductors. But even with that one, we have number of slots and number of conductors per slot. So the total number of conductors is just going to be 51 times 12. And then from there, the rest has been given to you, right? So please, I'm moving on because I am feeling very exhausted. So I'm moving to example 4. Okay. I want to pay more attention to the examples for the compound generator and the series generator. So I'm just going to skip this one. Please, you understand what I said about addressing this question? So please note something here, okay? For here, he chose A to be equal to 1, right? And then made P 2. So if you want A to still be equal to 2, then you use the number of poles, not the number of pole pairs. So for here, you could have made A 2, and then number of poles would be 4. But then 4 on 2 will still give us 2. So he made A1 and then used the number of pole pairs. That's what I was talking about before. Okay. So please, can I move on? Can I move on?
Yes,
Yeah.
All right, thank you. So example 4 says, let me see. 8 pole lap connected. So all you need to know here is that A is equal to P. So you are not going to include A or P in your calculations because they will cancel out, right? And this one too, we're given our EMF and we're asked to find our flux per pole. So same equation, just at this time, we are going to make our flux per pole phi p the subject, right? But because it's a simple lap winding, this and this are going to cancel out because they are equal, right? Then from here, you make phi p the subject, and then from there, you can just bring, the rest were given, right? You can just bring it in. Let me see. Oh, wait, sorry. You were given, how do we call it? We're given our phi p. It's this one that we are looking for. We are looking for number of, okay, so let me talk about this question, okay? Let me talk about this question. An 8-pole lap connected armature driven at 350 revolutions per minute is required to generate 260 volts. Okay. Is required to generate 260 volts. The useful flux per pole is about 0.05 Weber. If the armature has 120 slots, calculate the suitable number of conductors per slot and corresponding useful flux per pole. So, with this one, we were given E to be equal to 260 volts. Right. We were given NM to be 350 RPM. We're given Z, sorry, we weren't given Z. We're given phi p flux per pole to be 0.05 Weber, right? And we are to find Z. And we know that E is equal to Z phi p NM P all over 60A. But since this is a simple lap winding, we know that A is equal to P, right? So this and this will cancel out. They won't have any effect. Making Z the subject of our equation, we are going to have (60E) divided by Z phi, sorry, no Z. 60E divided by phi P NM is equal to Z, right? So substituting our values in, we are going to get Z to be approximately 890 conductors, right? Is are we okay? Okay. And then we know that we were also given number of slots S to be equal to 120, right? And then the question says, find a suitable number of conductors per slot and the corresponding useful flux per pole. Okay, so if this is what we got for Z, then small z is going to be 890 divided by our slots, right? So we are now going to get here 7.4 conductors per slot, right? And we want this to be an even number and we want it to be greater. So we are going to use, we want it to be an integer, right? So we are going to use 8 conductors per slot, right? And even because it's conductors per slot, it still has to be even. Okay, so we have 8 conductors per slot. Therefore, our suitable number of conductors is going to be 8, right? All right. So now we want to look at our useful flux per pole. Okay, so if our machine is identical, then Z old, phi old should give us Z new, phi new, right? Where our Z new is now going to be, we know we are picking 8 conductors per slot. So 8 times 120 is now going to give us our suitable Z new. And that is going to be 960. Right? So we have here 890 into bracket 0.05 is equal to 965, right? So we are gonna get here 890 times 0.05 divided by 960. All right, so now we are going to get here phi new to be 0.046. Okay, so our new useful flux per pole is going to be 0.046. Please, can I continue?
Yes, please.
Okay, so example 5. This example 5 talks about the comparison between lap and wave. Okay, so we are going to realize that for a lap connected, current is going to be 800, voltage is going to be 132. So for lap connected, as we've already spoken about, for lap connected, you get more current, less voltage for the same power. And then for wave connected, more voltage, less current, but still the same power. Okay, so let me skip example 5. You can check that one out on your own as well. If you check it out and you have any question, you can just reach out to me. Okay, so example 6 is also another very straightforward one. Everything has been given. Has everything been given? The only thing is that we have what? 144 slots, 2 call size per slot, 310. So that is going to be call size per slot, which is going to give us so to find our Z, we just multiply our number of slots by our number of call size per slot, and then by our number of turns. Okay, and then we get that we substitute everything in, we make phi p the subject. Okay, so once again with this one, if you have any issue, you can just reach out to me, right? So now let's look at example 7 for a DC shunt motor. Okay, I think for the shunt and the compound motor is where some people had been reaching out for some with some issues. All right, so I'm going to do example 7, 8, and 9, then we call it a day. And maybe tomorrow after church, I don't know. As I said, I'm not really feeling well, so I'm hoping tomorrow after church I'll be okay. Then we'll go through the DC motor examples and the exercises at the end of the slide, right? So if we don't have enough time to go through the examples at unit 1, you can just go through them on your own. If you have an issue, you can text me. Okay. So for shunt motor, the DC machine has a magnetization curve for 1000 RPM given by E is equal to 300 IF plus 1 plus IF. The armature circuit resistance is 0.12 ohms. The shunt field resistance is 247 ohms, and the machine is connected to a 230 DC supply. Okay. Calculate the load current of the machine when it is running as a generator at 1650, right? So with this one, what we are going to do is we are just going to calculate. We are going to look at our calculations at 1000 RPM, right? Then we can use proportionality to find our values at 1650, and then from there we can just, so I'm going to just go through this question real quick. All right, so it's a shunt connection, which means our circuit is going to be of this nature. Because we're given our terminal voltage, right? And here we have our field resistance, and we are going to have a current IF here, right? So for a shunt circuit, because it's in parallel, the voltage across this resistor is going to be the same as our terminal voltage, right? So our IF is going to be per Ohm's law. We know that V is equal to IR, right? And we have the voltage across our resistor and the resistance, the value for the resistance, which was given as 247 ohms, right? So our IF is going to be 230 volts divided by 247 ohms. And this is going to give us IF to be 0.93 amps, right? And we know that for our magnetization curve, E is equal to 300 IF all on 1 plus IF. So substituting the value of IF being 0.93 here, we are going to get our E at 100 RPM to be 144.56, right? Because keep in mind, this characteristic was generated when our generator was running 1,000 revolutions per minute. Okay, so then for the same field, for the same machine, E is going to be equal to 1650 on 1,000 times 144.56. What does this mean? All this means is that if everything is kept the same, then E nu, if we have our E at 1,000 being 144.56, then our E at 1600 150 is going to be if more or less divide proportionality, right? Please, are we okay with that?
Yes, please.
I want a response. Yeah, okay. Please, are we okay?
Yes, please.
Okay. So then our E at 1650 is going to be 238.52 volts. Right. So we'll just bring that back into our equation where we know that for a shunt, we have VA is equal to IA RA plus E, right? So if that be the case, we are now going to have IA, making IA the subject, we have V minus E all over RA, which was given in the question, right? So we still have the same terminal voltage, of course. So at a speed of 1650, we have E to be this. So at a speed of 1650, we're going to have our IA to be equal to we're going to have our IA to be equal to 71.03 amps. Right. Please, are we okay with that? Are we okay with that? Times itself. Please, I'm going to assume that we are all okay with that. Okay. And yeah, let me use. Okay. So please note this relation now. Okay. Maybe tomorrow or maybe even at the end of the lesson, I'll use this relation to explain armature reaction. Okay. So note this down somewhere. Right. All right. So example 9. Hey, example 8. For compound generator, it says it is desired to level compound a shunt generator so that the terminal voltage at full load of 100 amps. So this is load current, right? Is equal to that at no load. Okay. So please, with compound generation, with compound compensation, right? We can either have flat level compound where, so please let me try and see if I can explain this real quick before I go on. We know that V is equal to E minus IA RA, right? We know that E is equal to, oh, okay. I made a mistake somewhere here in my writing. The E was correct, but the writing was wrong, right? It's E minus V on RA, right? So you are still going to get the same thing. E minus V on RA. So, okay. So for compound compensation, we know that we have E minus IA RA giving us our terminal voltage, right? But for a shunt, so I want to teach all of this. Okay. So for a shunt connection, we are going to have the resistance of our field. We're going to have, oh, stop that. Okay, so for a shunt connection, right, we know that IF, once it becomes loaded, right, or no load, or no load, our IF is going to be maximum because whichever current comes from here is going to go through here, right? But once it becomes loaded, our IF is now going to share current with this branch, right? So once it becomes loaded, our IF is going to reduce. And for our relationship, VA is equal to EA minus IA RA. We also know that EA is equal to some constant K phi omega M, right? And we know that phi being flux is dependent on our IF, right? Okay, so if that be the case, then once our machine becomes loaded, IF is going to reduce, right? If IF reduces, flux is going to reduce. If flux reduces, EA is going to reduce, even before the voltage drop comes here and reduces our terminal voltage, right? So for a shunt connection, we are having a reduction in EA before the drop. So our terminal voltage is going to reduce by a lot more, right? So we are going to add another field in series to boost our flux, right? So that once IF goes down, our flux is still going to be boosted by our series field, right? So that EA can be at a certain higher level, such that once the IARA drop comes in, we can have a high VA. So we can have flat compounding, where we make the compensating field a little bit higher, right? So that our EA increases by a little bit, so that after IARA losses come in, we can have a VA at a similar level to our VA no load, right? This is done when the voltage VA is to be used at the site of generation, okay? But then for over compounding, we increase our IA to such a high level that our terminal voltage VA becomes greater than our no load voltage, right? And this is done when our voltage being generated is to be transmitted, okay? We know that if we transmit voltage, we are going to have transmission losses, okay? So if we have a high terminal voltage, once it's transmitted and once the losses comes in, wherever it's going to be used, now it's going to have a VR, right, now equal to our no load voltage. So that's pretty much the difference between over compounding and flat level compounding. So over compounding, we make our compensating winding produce such a large EA that our terminal voltage will become greater than our no load voltage. So that when we transmit the voltage after transmission losses, our voltage will now come back to our no load voltage. And then flat level compounding is when we make our EA slightly larger so that after IARA losses, our VA becomes equal to our no load voltage, right? So that our voltage can be used at the generation site. Okay, so now let me go back to the question. Okay, so it is desired that blah, blah, blah. Okay, it is desired to level compound a shunt generator, blah, 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 so that the terminal voltage at full load, right, at full load will be equal to that at no load, because you want the terminal voltage to be used at the generation site, right? When connected as a shunt generator, the field current had to be increased from 2.75 amps to 3.3 amps to maintain the same terminal voltage at both no load and full load. Okay. If the machine is to be connected in a long shunt, please, we have two types of shunt connections, right? For compound generators, we have long shunts and short shunts. Okay, this is long shunts, right? This right here is our long shunt, where the series winding comes before the shunt field, right? And then it becomes short shunt if we have our shunt field here, our armature here. And then after that, we are going to have our series field here, right? So this is short shunt, and long shunt would have been if the shunt was connected like this. Okay, so please, on your own time, you can read on short and long shunt. Okay. So okay, where was I? If the machine is to be connected in long shunts and the number of poles, the number of turns per pole on the shunt field are 1,200. So we have 1,200 turns. Calculate the series turns per pole required and neglect voltage drop in the series winding. Okay. So let's tackle the first part of the question first, right? Which is going to end. The first part is going to end somewhere here. The series turns per pole required. So let's take that one first. Okay. So the first thing we need to know is that for level compounding, the actual field current is equal to the field current at no load, right? Since EOC, since we are trying to get our terminal voltage to be equal to our no load voltage, right? So, okay. So if the question said, in order to get this condition, right, our field current was increased to 3.3, then what does that mean? That means that we have a certain number of turns, 1,200, right? And then a series current being added to our field current to produce an MMF in a new series field, right? So we know that MMF is equal to Ni, right? So at flat compounding, our total MMF being supplied is 3.3 times 1,200, right? Our total MMF being supplied is 3.3 times 1,200. So we have an MMF of about 3,960 being produced from all our windings, right? But then we know that our flax winding is only producing an MMF of, let's say, 2.75. I said flax, sorry. Our field winding is only producing an MMF of 3,300, right? So that means that whichever MMF we have here, like the difference in MMF, actual MMF, and the difference in our compensated MMF and our uncompensated MMF is going to be equal to the MMF being produced by our series field. Please, are you okay with that? Because in order for us to achieve flat level compounding, our total MMF must be 3,960, right? And then without flat level compounding, our total MMF was 3,300. So that means that whatever is left, or the difference between the two, is the MMF being supplied by the series field winding, right? So the additional MMF being supplied by our series field winding is this, right? Okay. And so if it is in long shunt, right? If it is in long shunt, then then our IA, which is our series, the current through our series field resistor, the current through our series field IA is going to be equal to our IF plus our load current, right? KCL, load current IF enters here, load current enters here. So the current in our series field is going to be our field current plus our load current, right? So that's what we have here. And then we still know that MMF is equal to NI, right? So now we know the I being produced in our series field. And we also know the MMF being produced by our series field. So from there, we can just get the number of turns being produced by our series field. And that's going to be MMF of our series field divided by our series field current, which is going to give us 7 turns. Okay. Please, are we okay? I'm assuming that we are all okay. So, referring to the figure below, long chance, okay. Our second part of the question says, the above machine after its conversion had a terminal voltage of 220 at full load current, and the resistance of the armature shunt is blah, 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 blah. Calculate the value of EMF being generated. So now we are going to calculate the EMF that was generated after compensation, right? We are going to calculate the value of the EMF generated after compensation. So for us to know that, from here, right? From here, if we take KVL, we can see that our V is equal to VA is equal to EA minus IA times our series field resistance, right? So we are taking this loop, okay? So that means that this resistance no longer comes into play. And we already know our IA. So let's go back to the question. The question says, the resistance of the armature, shunt, and series fields were, so 0.12 for armature, 80 ohms for shunt, and then 0.08 for series. But then here's the case, we don't need our shunt resistance, right? Because of the loop we took, we don't need our shunt resistance. So our R is just going to be our armature resistance plus our series field resistance, right? So we have here EA is now going to be VA plus IAR. We already know IA to be load current plus field current because our IA is the current coming from here, right? This is our load current. This is our field current. We have IA being load current plus field current, KCL, right? And then we have our RA being armature resistance plus series field resistance, right? Our terminal voltage V was also given in our question. And so from here, we can find our E to be 240.6, right? So we can see that for flat level compounding, we decided to generate at an E slightly greater than our no load current, so that once our IARA losses come in, our VA can be equal to our no load current. Okay, so now I'm going to move to example 9. Please, I hope we are all good. I hope we are all good with example 8. If you are not good, I'm moving on with example 9. It's not easy. Example 9 is also telling us that a DC shunt generator is rated at 240 volts, right? So that's our no load voltage, right? That's the voltage we want to be using now. So it's rated at 240 volts and has armature current, IE of 400 amps at a speed of 1050, whatever that speed is, with the shunt field excited. The OC curve is given by, so we have our OC curve here. The armature circuit resistance has also been given there, and there are 2,100 turns per pole. Okay, the generator is operated at 1,750, so that means that our E is going to be constant throughout, right? We are going to look at our generator at the constant speed, right? So find the series winding MMF required to give an over-compound characteristics at 250 V if the terminal voltage on no load is. So with this one, we are trying to generate a terminal voltage VA to be 250 because it's going to be transmitted, and then after transmission losses, we are going to have it down at 240 at the site of use, right? So with that in mind, right, we know that first thing that we can know here is that our no load voltage at no load, yes, at no load, terminal voltage is approximately equal to E. Please, those of you asking for the midterm marking scheme, I've not seen it, okay? The first time I saw your midterm questions was when he came to share them in class. If I'm to get the marking scheme, please, how do we call it? Ask your course rep, okay? I think David had some of the calculation questions correct, and then I think the ones he had wrong, I've already explained why they were wrong. So you can just you can ask David, and David will explain the answers to you. Okay. So yeah, at no load, V is approximately E, right? So we know our no load voltage to be 240. So if that be the case, then we can equate 240 to our open circuit characteristics to find our IF, right? So this IF that we found here is our field current at no load, okay? At no load, okay? So we are going to keep this for now, right? And then, the work is plain to you. So we also know our no load voltage, right? I don't even know. Let me try and draw so that you can understand me properly. Okay. So we have for no load, we know that V no load is approximately equal to E, right? And our no load voltage is 240. So 240 can be made equal to 435 IF all on 193 plus IF to find our no load IF. So our no load IF is going to be equal to 2.375 amps, right? Right. So we can use our no load IF and our no load voltage to find our RF. Keep in mind, our RF is going to be constant despite our load, right? Because on no load, our shunt generator looks like this, right? And we have our E here, which is equal to our no load voltage. So the voltage across, okay, we have our E here, we have our V no load here, and we have our RF here, right? And we have here IF. So our IF at no load, right, times our RF at no load will give us the same V no load because they are in parallel. The voltage across our RF is going to be equal to our no load voltage, right? So that means that RF can be equal to V no load on IF no load. And we are going to get our RF to be equal to 240 divided by 2.375, which is going to give us 101 ohms, right? So our RF is going to be a constant 101 ohms for our future calculations. So we can just note this down. And now, what's the question saying we should look for? The question is saying we should look for MMF, right? Okay, we know that MMF is equal to NI. Right? Let me see. Okay, but we don't have the current I flowing through our series resistor, our series field, right? So the whole point of this question is we are looking for the current I flowing through our series field. Okay, and then we'll use that times the number of turns that we were given to find our MMF. All right. So we are going to look for our E at full load conditions, right? Because we know that our full load, we are going to be generating a high E so that once our IA, RA losses come in, we can still have a high terminal voltage, right? So we know that, so what we know is that we know that V is equal to EA minus IA, RA, right? We've been given IA, we've been given RA. So we can find our E. We know that we want our terminal voltage to be 250, right? So EA is going to be equal to 250 plus 400 times our armature resistance, which is 0.019 ohms, right? So we are going to have here E is equal to 257.68, right? So this is our full load E. And then from here, from our full load E, we can find our full load IF. Sorry, from our full load E, we can find our IF in the condition E is equal to G of IF, right? So if we know that this is 435 IF on 1.93 plus IF, right? So we are going to look for the IF that is going to give us this characteristic at full load. So this is going to be equal to our E at full load, which is 257.68 volts, right? So making IF the subject, we are going to find our IFR, which is the IF that is going to give us this characteristic for our E, right? This at the beginning was like 100. So our IF that's going to give us this characteristic for our E is going to be 2.805 amps, right? And then we can also now look for our field current, our actual field current at full load. So we know that our field current at no load was V terminal voltage divided by our RF, right? And so now we found our terminal voltage. We found our RF, and we know that our terminal voltage is supposed to be 250. So 250 on 101 is supposed to give us our actual IF, right? Which is going to be the IF when our machine is in operation, right? So with this one, we are going to get 2.475, right? Okay. So with this, then the change in current or the difference in current between this and that is basically the current being supplied by our series field, right? Because to have an EMF of this, right? To have an EMF of this, we want our total field current, which is current from our series field and current from our shunt field, to be equal to this, right? And we know that current from our shunt field alone is just this, right? So that means that whatever is left for us to get this is equal to the current in our series field, right? So we know that MMF is equal to MMF of our series field is going to be equal to our series current times the number of turns, right? And our series current is going to be equal to our total field current, right? Which is the current being supplied by series field, shunt field, 2.805 minus the current being supplied by our shunt field alone, which is 475. So our MMF now is going to be, our MMF from our series field is going to be number of turns 2,100 times 2.805 minus 2.475, right? And we are going to get here, MMF is going to be equal to 693 ampere turns per pole. Okay, so that's the MMF being produced by our series field. Please, I'm going to end it here for today.